is the so-called genetic approach. There exists a genetic textbook in analysis, in fact, at least two, one by Toplitz and one by Kolmogorov. There exists genetic introduction to differential geometry by Michael Spivak, and so on. So the genetic approach, the idea of the genetic approach is that one tries to present the material.
So Toplitz, mechanical things called the second.
Toplitz
The second.
Toplitz is
But I don't. Toplitz is the one.
Godemov, the representation series, he has a course in analysis. Yeah, so and just the material in the course is presented the way it was developed. For example, the concept of Fourier series or maybe Bessel function from Euler to subsequent developments to Lagrange and so on. So nobody can ever try to do such thing for probability theory, because when one gets acquainted with the progress of probability theory, one is immediately very painfully aware how slow and gradual this progress has been. So probability theory is really very hard, and especially conceptually very hard. Вы записываете, правильно же? За все это, да? То есть потом можно будет. So the for example, when one considers calculus and how Archimedes was computing extremely sophisticated integrals, such integrals that if you give them to calculus students today, you will fail the entire class. So one can see how already the Greeks knew a lot of calculus that we know today and a lot of geometry. But with probability theory, it was really very gradual and very painful, and there are many examples of this. And I want to illustrate this phenomenon on an example of Kolmogorov axioms. So everybody knows that just Kolmogorov gave axioms for probability theory. So mathematical probability started with Kolmogorov. And let me start by asking my audience what this actually means. So what did Kolmogorov actually do? So let us hear measure. So the idea of measure theory existed for a long time. Measure theory, so let us recall that the book of Kolmogorov, it was published in German. The book it was published in German in 1933. The Russian translation appeared immediately. By the way, the title is interesting. The main concepts of probability theory. In Russian translation, the main concepts, not the main, not the theory, the main concepts of probability calculus. The main, it's usually translated probability theory, but the fact is, the main concept of probability calculus. Okay, so what did he change? So the measure theory existed, even in infinite dimensional space. This is 1933. Already Daniel has integral in infinite dimensional space. So clearly, measure theory was well known by 1933. So Ruslan says that independence, but independence was not introduced by Kolmogorov. Independence was there for a very long time. So what did Kolmogorov actually achieve? Why do we say Kolmogorov axioms? That, пожалуйста. 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 Володя. Рома, пожалуйста. Так, идем по старшим. Значит, Андрей знает то, что уже слышал. Да, что? Да?
The norm and axiom.
The what again?
The axiom of norm, the probability of the whole is a unit.
But surely it was clear that the probability is 1, right? Probability is up to 1. Surely this was not before Kolmogorov. It would not be classic discovery. So maybe in Zoom somebody can say, so what was original in the work? What was the main originality in the work of Kolmogorov? Maybe there are some suggestions in Zoom. Okay, so if any suggestions, please, you're very welcome to contribute to the lecture. Just say without hesitation. Okay, so let us go back. Let us wind back significantly in time, because in fact, the answer to this question is surprising, and it is, in fact, as I say, it is surprising in that it shows how things to which we are so well used were so very difficult to come up with, on the one hand, and on the other hand, how many things which even today cause a lot of difficulty to the student. Okay, so let us begin, let us go back to the Greeks. So the concepts of necessity and chance are found in the Greeks. Are found in the works of the Greeks. So it is Democritus and Leucippus. And in fact, the categories of necessity and chance. So the word necessity, there is always this problem with the Greeks that the words which they use are not the same as the words which we use. And it's especially true about words related to probability theory. And it is to some extent true about necessity, but it's especially true about chance. In fact, the Greek word, which is usually translated into modern languages by chance, modern languages, all of them have roughly equivalent words, случай in Russian. So this word in Greek,
the human mouse means happy.
well, that's exactly my point. That's exactly my point. It means fortune. It means, in fact, divine providence. That's exactly my point. It means divine providence. It means, so you say happy, but happy, there are many words for happiness in Greek. It means happy in the sense blessed by God. So of good fortune, of good luck. We can also say today also luck and chance. In fact, in French, for example, quelle chance. Luck and chance have some similarity. But in fact, the important point for me is that this is will of the gods. There are some anarchy. This one is, I think the translation is reasonably accurate. So, with the usual point that these translations are always approximate. Greek words are just very different words in modern languages. So, but my point is that so chance. So how do I say? There are things that happen of itself. So if I drop this chalk, it falls. But sometimes God intervenes directly. There is action of God, and this is chance. This is chance in the Greek world. So necessity and chance are not oppositions. So they are in a complex relationship, which is not necessarily that of opposition. And already in the Greek philosophy, we can see the conflict which will develop in the theory of probability for a very long time after the Greeks, and we can say that it's continues even today, as with all philosophical conflicts. So this is the conflict between objective probability and subjective. I didn't. Okay. Objective probability. Yeah. Objective probability and subjective. So this conflict is best illustrated by a clear example, well known and often called the St. Petersburg roulette. So imagine just that here in the main court of Fistiach, there is a pavilion. So the rules of the game are as follows. You enter the pavilion and immediately you get a room. And then a coin is tossed. If the coin falls head, then you get out of the pavilion, it's end of the game. If the coin falls tails, you get 10 rupees. And the game continues. Then there is second toss. If the coin falls head, you walk out of the pavilion, end of the game. If the coin falls tails, you get 100 rupees. And so on. So sometimes you get 1,000 rubles, then 10,000 and so on. So a simple computation, just for elementary probability classes, that the expectation of your gain is infinite. Would you be willing to exchange your flat against the entrance to this pavilion? You could possibly win all the money in the world, but with very low probability. So calculus of probability theory, and this is well known fact in insurance or investment. Calculus of probability theory does not represent what people actually do. So people don't like high risk, high gain games. They're not willing to pay what they stand to win. That's a gain. So the high odds overweigh the fact that with low probability there might be very significant gain. So that the question comes, does chance actually exist? This is illustrated by Aristotle, for example, in the question, is there going to be a naval battle tomorrow? Is tomorrow going to be a naval battle? I mean, there will be, there won't be. But the question is there an authentic uncertainty in this? Or is this just a question of my lack of knowledge? So I don't know if tomorrow it will snow in Moscow. Well, I'm afraid I know actually, but let's mention it. So whether in Moscow it will snow or not, or whether it will be sunny day or not, I don't know. But in fact, if I consult the forecast, I do know, and with, let's say, with a reasonable degree of certainty. So the fact that I do not know is a representation of my knowledge. It's a statement about me. It's not a statement about Moscow. On the other hand, what will happen with weather in Moscow in a month? Nobody knows. So what will happen with the weather in Moscow tomorrow? I don't know, but Ruslan can Google it and he will know. But what will happen with weather in Moscow in a month? Nobody knows. So the time, as we saw very clearly today, the time it takes to get from downtown Moscow to here. Well, when you start the trip, it's one time, and when you finish the trip, it's another time. But the point is it a statement about me that something I know, something I don't know? So I don't know Ruslan's birthday, for example, but he can tell me, I will know. So right now, I can say, which month was Ruslan born? So I don't know. I can try, let's say, June. Now, which months were actually born? February. Okay. So you see, now I know. So now there is no point. Now there is no point. It's clearly a statement about me. So when we say that there was probability 1/12, it's because I didn't know. It's clearly. It's not that Ruslan could have been born at a different month from which he actually was born. He was born in February, not in June. So, and this is the very point of subjective probability. So the question is whether there is, so it is very clear, nobody will doubt it, that subjective probability exists. There are situations when clearly something is known, but I don't know it. It's clearly known, but just I don't know. So I don't know, when there are exam questions. So in Russia, exam questions, at least traditionally, they are put on the table, and you don't see which one you pick up, like cards. Or in fact, you put a card, and then I pick up one, and so I fall to some question. But in fact, the teacher who put the tickets, he does know which question is where. So this is clearly subjective probability. The question is, does there exist something else? So Bernstein, who we will meet in more detail a little bit later, he gives a very nice example. He says, when I walk out this room, I will take the stairs. I will not walk out the window. At the same time, it is quite possible that on the stairs I fall and break a leg. It's possible. Such things happen. People fall on the stairs. Conversely, it is also possible that such things happen, that people jump out the window and don't get injured. It is possible. It happens. So, but yet I will certainly take the stairs. I will not walk out the window. It's not a question about degree of my knowledge. It's clearly something about the world, not about me. So this gives the, so this with this argument, Bernstein achieves two aims. First of all, probabilistic reasoning. In fact, every decision involves some sort of probability. And secondly, it is a little bit difficult to argue that when I decide to walk out the room and not jump out the window.
There were so many people with surname Bernstein. So
Sergei Natanovich, we'll get back to him. We'll get back to that. Sergei Natanovich, the one of orthogonal polynomials and classical analysis. Sergei Natanovich is a member of the Academy of Harvard. So yes, so just it's a little bit difficult to say that it's just a matter of opinion. It's not a matter of opinion, it's a matter of analyzing the world. I'm clearly doing the right thing, I'm taking the right decision by walking out the door and out the window, right? So clearly there is something more about just than just the state of ignorance. So, and this philosophical debate, which starts in antiquity, and as very often happens in pre-Socratic, so the point of view of pre-Socratics, well, in this case, the atomicists, is closer to us than the point of view of Aristotelians. That, in fact, that necessity and chance are not so mutually exclusive. Necessity and chance somehow intermingle. This view of the pre-Socratics is even closer to our view today, that, as I say, the view, for example, of Aristotelians, according to which everything has a cause. So to wrap up, it could be great subject for a separate lecture, determinism and chance in Greek thought, but this is not the subject of this talk. But just to wrap up, let me point out that there is this famous quote from Laplace, which goes from text to text, that somehow where Laplace says, if an intellect is powerful, and I should say immediately that I translate from what I read in Russian into English as I speak, and the original is in French, so maybe the exact wording is not similar, but the idea is very clear. So if, says Laplace, a powerful enough intellect were able to see all the positions of all the particles and all the forces, then he would be able to predict all the future and all the past, to the infinite future and to the infinite past. So this is clear expression of determinism. What is less often mentioned is that Laplace takes it direct from Cicero. And since Cicero was not exactly a mathematical physicist, probably Cicero takes it from somebody else, but we're not sure from who. It's very probable that one has to keep in mind that Cicero had.
Cicero русская там даже как
Yes. The guy, yes. De facto, it's not, yes, on fate, on destiny. So this is one thing, and the other thing that we all know about Brownian motion. But so okay, let me ask. Well, Ruslan already asked, let me ask that here. So, which is the first description of Brownian motion? Where does it occur? Who was the first to describe Brownian motion? Not Cicero. And not Brownian. Roma? Олег? Руслан смотрел на нас. Я не очень думаю. Кто первый написал по-русски движение? Понятно по-английски? Вы тогда спрашиваете, если что. Тогда спрашиваете, я повторяю. No, much. No, we are in antiquity. No, much. There is very famous description of Brownian motion in antiquity. In fact, it is due to Lucretius. If you Google Brownian motion Lucretius, you will see. So there is it's translated into Russian. Of course, you will see there is very clear description. In fact, Lucretius describes Brownian motion by saying that when a sunlight enters a dark room, then the particles of dust they make chaotic motions, and you can see that. And this is clearly a representation for Lucretius of chaos in nature. So, this the point of this is just to say that this complicated interplay between determinism and chaos is already, with all points of view that are possible, is already amply represented in Greek thought, in Greek thought, and as it is transmitted also by the Romans. Okay. So now, after this brief introduction about the Greeks, we make a major jump. So let us, by the way, since Ruslan mentioned independence, let me ask one more question. Just half digression, but half not. You mentioned, Ruslan, independence. So who introduced independence? There is clear, in history of mathematics, it is not often that we can clearly pinpoint an idea who introduced multiplication of probabilities, but here there seems to be a clear answer. Independence. Who introduced independence? Multiplication of probability. Who introduced the concept of multiplication of probabilities?
Mathematician.
Yes. Yes, it's mathematician. Yes, it's a mathematician.
Looks like medieval Europe should be medieval Europe. Like our case.
Good guess, but he has a precise name. Andrei. Or you know. Maybe there is French Karas. Нет, раньше Karas. Да. Гораздо раньше. Нет, у вас это правда. The name was Cardano. And Vice is completely right. It was Girolamo Cardano. Girolamo Cardano. And indeed, in the context of card games, he has a practical book. But Cardano was an extremely prolific writer. Prolific.
Giro in I, not E.
I think it's both, right? Okay. Because it's Hieronymus, so sometimes it's the I, sometimes it's the E that is something. So he wrote it Latin. So prolific writer. Cardano understood that, and quite correctly, that to become famous you have to write it down, write down things. So just to illustrate how famous Cardano was in his day, let me point out to you that famously Prince Hamlet, when he comes out on the stage to pronounce the famous "to be or not to be," he holds a book in his hands. Which book is that? It's a book by Cardano. Cardano has a book on dreams, where more or less all the monologue in prose, yes, but it is all there. What dreams shall we see?
What are you reading? Words.
No, not this one. To be or not to be.
Oh,
What dreams shall we see and so on? Yeah. To sleep, perchance to dream, as there are. This all comes from Cardano. And Cardano was in fact very famous in Shakespearean England. So it is very reasonable to think that Shakespeare read Cardano because it was a bestseller. The book on dreams was best-selling, and so he gave it to.
was Prince for it or Italian?
I think this one. You catch me there. I think this one was Italian. I have to check. I think this one was Italian because it was popular. It was more popular. In fact, it is your question is completely valid because, in fact, educated Englishmen did speak Italian, and well, Latin maybe not so much. Famously, Shakespeare's Latin is supposed not to have been very good because the way he puts Latin names in his plays suggests to some researchers that he was maybe not very clear about how Latin interacts with groups. So, but Italian was the language that they did speak, in court and around the court. And in fact, Giordano Bruno, for example, writes his works in England. In England, he writes his works in Italian. When he goes back to Germany, he starts writing again in Latin. But when he's in England, he writes in Italian. So I have to check, but I believe that this is in Italian. So this is an excellent question. Okay, but so mathematical probability starts with Cardano with his book on games of chance. It is translated into English. You can find an English translation. It's, of course, you can also find original Latin. And now it's all digitized. But so it's a practical book. It's a practical book. How to win at cards? What are probabilities of different outcomes? How to understand that your partner is not honest? There's a special chapter. What are indications that your partner is not honest? So it's a practical, and then there are computations of probabilities, and then there is multiplication of probabilities. And this is how independence comes into play. So there are some generous readings of Cardano. If you read him very generously, you can say that maybe even the idea of the large numbers is there, but okay, but this is very generous reading. So we jump over Cardano, we jump over Bernoulli, we jump over Pascal, of course, and Fermat, we jump over Laplace, and we land in the Russian school of the 19th century, especially the school of Chebyshev. So then, as now, Russia had two cities. So Moscow and St. Petersburg, in fact, St. Petersburg and Moscow. So the school of mathematics, the main school of mathematics was in St. Petersburg, a school that had been started by Euler. One should not forget that the teacher of Lobachevsky, not exactly the teacher of Lobachevsky, but, well, the teacher of Lobachevsky was exactly the teacher of Gauss, but the one who hired Barthes was a student of Euler. So Euler did not really teach many mathematicians, but he did teach very capable administrators of mathematics. And gradually this work bore fruit. So of course, Lomachenko is a complete miracle. Lomachenko just the Emperor Alexander I opens the university in Kazan, and Lomachenko comes out immediately. So this was a miracle. In any event, in St. Petersburg, there is a well-formed mathematical school by the 19th century. And the main difference, this cannot be emphasized enough, the main difference between the St. Petersburg school and everybody else, it's not that probability was not done. Well, Gaussian distribution is called Gaussian distribution for a reason. But in St. Petersburg school, probability was considered a branch of mathematics. One should not forget that the law of large numbers is proved by Bernoulli in 1713 completely rigorously. But later on, probability theory was understood as a branch of natural science, in particular the Gaussian law. I mean, of course, not the Gaussian law as such, the Gaussian distribution as such, but the fact that mistakes obey the Gaussian law. This was considered a fact of natural science. This was not considered a mathematical science. This was considered a fact of natural science. You know, just force of gravitational attraction decays as inverse square. It's a lot of natural science, right? So mistakes, and it was very important, by the way, why it was very important to the Gaussian law to analyze mistakes in astronomical measurements. This was the age of astronomical measurements, so there were new, very good telescopes, and it was very, but it's considered as a statement about natural science. So probability was, Euler was doing some probability, it was demographic, there were many important uses of probability. But Euler, it was mainly combinatorial probability, and in Europe, it was mainly probability as natural science, statistics, demographics, what is age distribution and such principal teacher. So, but it was not, it is the specificity of the St. Petersburg school that in St. Petersburg, they were actually proving things. And it was very difficult. So, because famously, precisely the central limit theorem, Chebyshev proved it. Well, I don't want to enter this controversial terrain, but let us say that at the very least, the proof was incomplete. So there were some, it was a big problem. Proving the central limit theorem is very hard. It was a big problem. But Chebyshev gave his famous proof of the law of large numbers based on Chebyshev inequality. It's much simpler. So Bernoulli's proof, let us recall how Bernoulli proves the law of large numbers by analyzing large deviations. He proves the fact that away from the average, the probabilities decay exponentially. So if you have a fair coin and you make 100 tosses, then if you have 1% more heads than tails, this event is exponentially improper. Exponentially improper. This Bernoulli proved. It's a simple exercise. One can, it's possible to explain in school. It doesn't require anything non-elementary. But the conceptual argument of Chebyshev, this was completely different level of sophistication. And the proof, let us not enter the discussion correct or not correct, with corrections, with gaps. Proof, for what it's worth, by Chebyshev of the central limit theorem, using the moment method, it was at least a conscious attempt to prove the central limit theorem. Still to prove the central limit theorem. Then there were his students of Chebyshev, Labanov, Markov, who were improving on this. Then there was the method of characteristic functions. Then there, of course, the Labanov condition in the central limit theorem. It's still taught today in courses. So there is this whole, shall we say, analytical approach to probability theory. It is very important to realize that there were no random variables. This is my key point. There were maybe trials and outcomes. There were no random variables. No random variables. There were trials and outcomes. Okay. So this is what was happening in St. Petersburg. There was this very brilliant, really brilliant, with very, how should I say, a very forward-looking mathematical outlook on probability, with a very sharp understanding of the formulas that would come into it. In particular, it is Chebyshev who introduces the notion of orthogonal polynomials. So you might say, well, orthogonal polynomials are resolved, polynomials of Legendre are in fact appear in the work of Legendre, and I think even before that, the work of Euler. What's the point if Legendre already considered? So the point is that the very concept of general formulation of the problem for solving polynomials, this is Chebyshev. So polynomials are introduced by Chebyshev. So this towering St. Petersburg School of Analysis, this is St. Petersburg, and now we come to Moscow. Okay, so St. Petersburg. Для русской публики, если что-то непонятно по-английски, спрашивайте, пожалуйста. Все понятно. Точно. And Moscow. So here we have Chebyshev. Moscow.
Markov Senior, by the way, Andrei Markov Senior was the father of Andrei Markov.
That's exactly right.
That we know from modes, rates, and many other things. Yeah.
That's right. That's exactly right. Yes. That's good. So the situation in Moscow was completely different. So Moscow was a very provincial city. You can see it already in War and Peace, for example, that when things happen in St. Petersburg and when things happen in Moscow, it's not the same. It is very clear, for example, from the following well-known fact, that the Swan Lake of Tchaikovsky, nobody has the slightest idea what was the Swan Lake of Tchaikovsky, the way it was produced in Tchaikovsky's lifetime, in particular, whether it was happy ending or not. It's conjectural, not, but there is no clear indication fact. Why is that? Because it was in a provincial city, Moscow, and it was in a provincial center of the Bolshoi. So nobody bothered to describe the performance in detail. So we don't know because there is no description. It was not a major event, the premiere of the Swan Lake. So when it was premiered in St. Petersburg 15 years later, that was a major thing, but Tchaikovsky was already dead. So just in Moscow, it was rather a provincial setting with some very good mathematicians, notably Peterson, the geometer, Peterson, Peterson. So,
well, if you ask Monica, he will strike Peterson away and say only Kodats.
But we won't. We will not do that. So Peterson, and just importantly for us, Bugaev, the father of the poet Andrei Bialy, and
actually created. He was the dean of the Moscow University, and also who created Mass-Bornik journal.
That's what I'm coming to.
Yes, and by the way, the main university, the main popular university was anyway in Moscow. There was no university.
Yes, there was. Yes, but
Yes, but the St. Petersburg University was just a school for a group of foreign academicians and their students. It was not a university in the proper sense.
But the academy was in St. Petersburg, and the big shots were in St. Petersburg. It's how to say it, center of the mathematical establishment. Astrakhanatsky was in St. Petersburg. Moscow was somehow the backwaters. So, and the figure of key importance for us is Nekrasov. It is quite amazing. Have you ever, Nekrasov, obviously not a poet, but a mathematician. Have you ever heard about Nekrasov, the mathematician? Well, precisely, there is no surprise. In fact, it's quite amazing how such a major figure is so completely forgotten. Pavel Alexeyevich Nekrasov is a student of Bulgaria. And he started in complex analysis. It's quite classical. He started in complex analysis. He did some work on approximation theory, which was still quoted in the Soviet Union. In fact, that's the work of his that was quoted in the Soviet Union. He had work in saddle point method, where he gets results roughly. Well, this is the whole point of the problem. I say roughly equivalent, but both words are important. Roughly equivalent to the much later work of Debye. So Debye is the one, the famous author for giving the saddle point method its modern treatment. Let us recall that what Debye in particular considers Bessel functions. Considers integral of the following form. Over a specifically chosen contour that may not get this, that the contour has saddle, then it has descent from the saddle and so on, Debye. So in fact, Debye needed Bessel functions for a specific problem for which he got the Nobel Prize, but it's also a very important mathematical problem, and treatment of Debye is essentially without changes goes into modern treatments. So it's what is, if one needs such type of integral, one can use for Debye, even today. It has been improved, but it is it's still quite relevant today. So Nekrasov did not, in some sense, his treatment is better, in some sense, his treatment is worse, but it's important to keep in mind that it's 30 years before Debye. So he comes up with saddle point method 30 years before Debye. Then, and this is most relevant for us, he comes to probability theory and to the question of the central limit theorem, on which the St. Petersburg school is working very actively. Now, mathematicians are often territorial. This is not a surprise. It was true then as it is true now. There starts a very bitter exchange over many years between Nekrasov and Markov. So this exchange is heavily politically colored, in that Markov was a famous, famously of liberal convictions. The most famous illustration of the convictions of Markov is that when Tolstoy was excommunicated, Markov wrote a special request to the Holy Synod, requesting that Markov be excommunicated too. By the way, Markov waited. He didn't do it immediately. Markov waited because he wanted to retire from the university. Otherwise, it would not be possible. Being excommunicated, it would not be possible to continue his teaching career. But by the time he finished his teaching career, he wrote a request that he shared, pointing out that he shared the convictions of Tolstoy and that he did not believe in the dogma of Orthodox religion, so he had to be excommunicated. It was obviously a major scandal. This is 1912, so the Russian Empire is on the brink of collapse. It was major scandal. A mathematician of great international glory asked for his own excommunication, and also how do I say? It was not just a private matter. The Russian Empire was not a secular state. It was a state with a government religion, and in particular, public servants all had to be of the Orthodox religion. So it was also, the civic rights of Markov were also downgraded. If you were not a member of the Orthodox Church, you could be a member of a different church, but you could not be nothing. So you lost civic rights. You lost in civic rights. So it was really to some, how do I say? There is some, let me put it this way, there is some similarity between this and, let's say, burning one's passport or something like this. It is not purely a matter of private conscience in Russia. So there was this huge scandal. The newspapers, the newspapers picked it up. The church tried to do everything it could to avoid the scandal. So obviously, well, there were also kinds of tricks. The Bishop of St. Petersburg said that this is not a question for the bishopric, but in fact it has to be referred, or no, maybe not this way. So it has to be referred to maybe who it was, the Oberprokuror, the overseer of the Holy Synod. The overseer of the Holy Synod referred the matter to the Holy Synod, and the Holy Synod referred the matter back to the bishop. So there was this classical bureaucratic circle. So the church did everything somehow to avoid messing with this. But Markov was a very determined man, and so he went one circle, and then he went full circle of this bureaucratic back and forth, and he insisted, and at the end of the day, he was formally excommunicated. So because the scandal was growing too much. So Markov was a man of this type of conviction, and he was excommunicated. He was excommunicated, yes. So, and whereas Nekrasov was conversely an Orthodox Christian monarchist, but also a public servant of great distinction. He was president of the Moscow Mathematical Society. He was minister, maybe deputy minister, but I think minister of public education. He was rector of the Moscow University. So he was very distinguished public, not just public servant, but very distinguished public servant. And this, everybody knows that it's very difficult to combine mathematics and administrative service. So he was clearly a man of great mathematical talent. He had fantastic intuition. But it is also clear that his formal training was maybe not his main strength. So his papers are published and digitized, you can Google them. So if your student for an exam writes this, you will pay. It is not, strictly speaking, this is not mathematics. So clearly you could not refuse to publish a paper of the president in a journal of Mathematical Society. You could not refuse a paper of the president of the Mathematical Society. But in fact, the papers have fantastic ideas. So the papers have this drawback that often comes up. If you read them generously, there is a lot of them. If you read them ungenerously, they fall apart. So Markov, in his criticism, he was right. He was right. There were, strictly speaking, mistakes, or maybe not even mistakes. It's in a sense even worse. It's written in such a way that it is not obvious. You know, mistake is when you have minus sign, but you have to put a plus sign instead. But the way Nekrasov's papers are written, it is not obvious what you have to put instead. On the other hand, if you do give him the benefit of generous reading, then there really is a lot. There is a lot. In particular, Nekrasov is an absolute pioneer, and this is in pure mathematical terms, because you see, saddle point method. Saddle point method, the step of Nekrasov is important, but you cannot really call him a pioneer because saddle point method, it was present in the work of Blas in some form, in the work of Riemann, of which maybe Nekrasov was not aware, at least he doesn't quote Riemann, but Debye certainly was aware of Riemann. But here, Nekrasov is an absolute pioneer in the subject of local limit theorems of the theory. So, do you know what it is local limit theorem? From локальная предельная теорема. Пожалуйста. Let us, audience participation question. By the way, in Zoom, please don't hesitate. If you have questions, comments, or any contribution of any kind, please don't hesitate to say.
I think finally we will end up with a lower slope limit.
Well, no, maybe not. Maybe not today. So local limit theory, what does it mean, local limit theory? So, okay, let us recall that the central limit theorem, let me consider just the case, let me consider different case from what was considered by Nekrasov. I consider the case as was considered by Hinchel later, but it is just more immediate. Let me consider random variable with density. So let me consider some. Let's say that well, I write in moderate notation that the expectation is 0, the variance is 1. So I consider the sum of these independent variables. And then the central limit theorem of probability theory says that it converges the distribution to the normal distribution. What does it mean analytically? It means that the probability that this sum, 1, S, let's say S. The probability that Sn is between A and B converges to, is roughly equivalent, in fact converges to, well, the probability that we all know. The problem of the local limit theorem is the problem of probability density. So the probability conversion was about probability density. Плотность вероятности. Сходится функция распределения в центральной предельной теореме. Центральная предельная теорема – это утверждение о сходимости функции распределения. А как насчет плотности вероятности? No, exactly. That's why I just okay. I address this in a moment. But let me just state like this. So the local limit theorem is the question about convergence of the probability density. The probability density itself is the Gaussian density, yes. And this is a much subtler theorem than the central limit theorem of probability theory. And to the best of my knowledge, the first theorems of such type are due to Hitchin, but it's 1920s. Nekrasov has a little bit different setup. So he considers discrete random variables assuming discrete values. So obviously, discrete values, he does not consider the probability of, so discrete, let's say integer values. So obviously, he does not consider the probability of this thing assuming this specific value. He considers an interval of values. But the interval is very small. So here, the interval would be 1/n to alpha, where alpha is something like 1/6. So it's very small. So it's a little bit in between. So it's local, but not so very local. But it's completely novel formulation. This is 1884. It's completely novel formulation. So the St. Petersburg mathematicians, they tore Nekrasov apart. they were very harsh. Just to give, it's a little bit difficult maybe to render in English, but one paper of Markov is called Отповедь Некрасова. So Отповедь is a harsh word. It is rendered in English approximately by refutation, but it carries in Russian a strong, a strong connotation of, I don't know, let's say somebody being rude on a bus, and you tell him not to be rude, something like this. Strong connotation of the guilt of the person to whom the refutation is addressed. I don't think I can give a translation immediately, but the point is that this is not a word for academic discourse. I think it's maybe the only time it was used in, and one should not forget that the establishment positions don't play out very well, because it is clear that Nekrasov is an public servant of distinction, but it is also clear that Markov is one of the most famous mathematicians of his time. So even today, imagine a conflict between a famous academician and somebody working at the Ministry of Education. So it's just exactly what newspapers love, right? So, but the point is that it is true that Nekrasov's work was not rigorous. As I said, if you get an exam paper written on the level of rigor of Nekrasov's work, you fail this exam. You will fail this exam. So it is not written on level of rigor that you would expect of a competent mathematician. But this should not obscure the fact that the ideas are really fantastic. Both the idea of the 7-point system and the idea of the local limit theorem, which is there formulated very clearly, maybe not very clearly, but shall we say very explicit, very explicit. It does require some work of verification, but it is very explicit, very explicit. So now I come to the other.
So why is there now citing St. Petersburg school, but not citing Moscow?
This is not a question you should maybe ask him. So just to say one more thing, Nekrasov had another drawback. He could not express his ideas clearly and precise. So this local limit theorem, it's a series of, I forget, so there is 10-page note with reasonably clear formulations. And then there are maybe like 200 pages of notes after notes after notes after notes of proof. Nobody read. No, I don't think even people who write us read that. Nobody can read it. It's impossible. It's impossible. Nekrasov was intolerably verbose. So he did not really have an impact. Regrettably, he did not have an impact on his contemporaries. He did not leave a school. He was ridiculed. He was a deep and original thinker. And he did not have an impact that he deserved to have. This is actually quite tragic. He also had, it is true that he had philosophical ideas that one may or may not sympathize with. It was very popular in the 19th century. He's by far not alone in that. It was very popular in the 19th century to envision applications of probability to the questions of ethics.
How much time will you need to reach Kolmogorov?
We're almost there. So we're almost there. So Borel, you see where Borel writes even in such terms that just what is the probability that such and such is a good man. So today it sounds, it's not a question that is discussed in today's probability textbooks. But 100 years ago, there was a lot of optimism of applying natural sciences to the real world. And Nekrasov is very much part of this idealism, of this set of ideas, and specifically one of his ideas, which I think has been realized already in the new millennium, at least in Russia, is his idea of teaching probability in school. Teaching probability in school. It is true that it is expressed as part of a philosophical agenda, precisely, roughly speaking, that a good, roughly speaking, and very much shortening. So, I very much abbreviate the contribution of Nekrasov, because if I quoted him to some extent, we would not be out by midnight. So, but just this is why I'm shortening as much as I can. So, just he says, roughly speaking, that a good man, an ethically good man, must know probability theory. If he doesn't know probability theory, there is no chance that he will be a good man. But in short, he says very clearly that we should teach probability in schools, and he says, this is quotation, it would be so nice to do such things.
So there should be some probabilistic counterpart of ariometros metis. So
That's exactly right. That's exactly right. But unfortunately, it's impossible, because the word probabilist does not exist in Greek. Probability, by the way, probability is a word introduced by Cicero. The word probable, probare means to, means to try. No, not try. No, to palagat, to put, to define, to pose. Palagat, something plausible. It's plausible, something that can conjecturable, something that can be put forward. Or probable. It's probable. It's the same root with probity, honesty. So probable means something that can be honestly thought about, something like this. Probable. Well, in short, so just precisely to reach probity, you need to teach probability. This is the idea of Nekrasov. It did not. Yes, and his idea was. He writes that it would be so nice to introduce this in 1913, where the 200 years of the Bernoulli law such numbers. But this was not to happen. There was a commission of the Ministry of Education, but there was also a lot of resistance of the St. Petersburg Academy. So in short, this idea, please correct me, but Ruslan, you went to school in New Millennium, Dasha, yours, right? So did you have some probability in school textbooks now, right? I think you did not have it. I think a little bit like binomial formulas, like that, or in coin tosses. I think sometimes I think there is none, maybe not obligatory.
But
Nekrasov also, by the way, he has a program. I saw this program. Yes, exactly. It's more or less. I mean, if you think about it, let's take as an example. We have to teach probability in school. So what do we teach? The answer is more or less obvious. There are not 500 possibilities what to teach. So that's exactly what he writes. That's exactly what he suggests. So the actual program that he suggests is completely reasonable, and it's more or less what we teach today. Because in fact, what else would we teach? That's exactly what that's precisely what you will do, and that's precisely what he suggests. But this was not to happen. So his program is not successful, and it is probable that Kolmogorov knew Nekrasov. It would be reasonable. Nekrasov dies in 1924. He should have known Nekrasov, but it does not seem probable that there was any specific influence. And of course, in Soviet Union, Nekrasov was not mentionable. He was not mentionable. He did not exist. For example, he's not part of the He was rector of the University of Moscow. He was rector of the University of Moscow.
When did he leave in some?
Well, yes, it's in 24.
Oh, okay.
Yes, so I don't know what happened to him. I don't know, but I imagine that if something really bad happened to him, probably he would be known. So I hope that he probably lived in some sort of obscurity. But I want to point out that so this rector of Moscow University, he was not mentioned in the big story encyclopedia. He just did not exist. It was cancel culture before the day. He did not exist. So then there was a certain revival, by the way, started by Australian historian of mathematics, Seneta. Seneta is the historian of mathematics who resuscitated Nikas. Say again?
With T, not K, as in Roma. I heard the surname of.
No, Seneta, not like Seneta.
Okay.
No, not the wrong guy. No. Okay, so he is the one who wrote about Nikas in the 1980s. Okay, so this Moscow school then experiences a real explosion with the next generation. So this is one of the most amazing phenomena in the history of science. So the next generation, Yegorov and Luzin. So far, this is very nice, but also quite provincial. With the next generation of Moscow mathematicians, Yegorov and especially Luzin, Moscow mathematics school becomes the best in the world. So it is not. It would be a fantastic lecture, separate about the Luzin school and so on, but this is not the subject of today. But I just want to point out that two students of Luzin, Hinchin, whom I already mentioned, and Kolmogorov, they start a seminar on probability theory in the 1920s. And now I come precisely to the context, to the setup for the actual book of Kolmogorov. So what was there? What was there when the book of Kolmogorov appeared, and what was so coming back to the question where we started? What was the main novelty? Where from came the impact of the book? So there was this seminar of Hinchin and Kolmogorov, and they wrote beautiful papers in the 1920s. So the first papers of Kolmogorov on probability theory are in collaboration with Hinchin. Especially these are papers related to the famous law of the iterative logarithm. So this was there.
Law which?
So again, the school of Luzin and Yegorov was a school with very, how shall I say, with very strong foundation in measure theory. So in real analysis, in descriptive set theory, in this new measure theoretic mathematics, they really knew this stuff well, as opposed to, for example, their comrades who were first and foremost analysts. So descriptive set theory, metric geometry. Also, it is very important to stress and emphasize Kolmogorov from his early age, and this is something that has no counterparts in St. Petersburg, was greatly interested in foundations of mathematics. And this interest in foundations of mathematics, it precisely comes from the philosophical interests of the founders of the Moscow school, Bugaev and Nekrasov. So the interest in philosophical implications of mathematical knowledge was very much a Moscow thing, not Thomas, very much a Moscow thing. So Nekrasov, when he writes, Nekrasov has a special historical paper. It is digitized, one can read it, which is precisely called Moscow Philosophical Mathematical School. It's a paper for the anniversary of Bugaev, his teacher, and precisely he develops a philosophical program of position of mathematics in society, in the system of education, in government, so in short, a broad philosophical mathematical program, quite typically for the Moscow school. Okay. Kolmogorov already has work about foundation of mathematics. He has famous work about the principle of tertium non datur, where he explains intuitionistic mathematics in terms of classical mathematics. He has important and, in fact, classical contribution to logic. I emphasize that his contribution is mathematical. It's mathematical work. It's interpretation of intuitionistic logic in terms of classical logic. Okay. He has worked in probability theory. He builds on work of predecessors. So the first mathematician to propose axioms for probability theory is Bernstein. Okay, so he had several predecessors.
Well, if we have to define approximately, so how long you're right. So of course,
We can also let's take a break, and who wants to leave can leave. Let's take like 3-minute break, and who doesn't want to?
I think it's reasonable. I think it's reasonable.
And then we can.
And now, let me ask a couple of questions. I don't have an intent to leave. Actually, we had a talk by the one lawyer about the work of Margaret Hadid, and the two, I think, 2 years, 2 hours and a half.
Well, it would be
For Moscow school, everything is possible.
so. Well, I think it would be strange if my talk were shorter than my lateness. So.
Yeah. Okay, so let's make a break. Есть вопрос. Два вопроса. I have 2 questions, maybe during the break. So first of all, есть ли какой-нибудь связи вот этих работ по вероятности, которые идут до конвея, потому что конвей сделал кучу всего в теории игр, и мне интересно, вот, есть ли что-нибудь вот идеи, которые выходят на конвей.
Да, конечно, мы как раз про это говорим. Оставайтесь с нами.
Чудесно. Нет, я останусь, мне так сказать, я же куда уже. Вот. Второй вопрос. Well, на самом деле, so my second question is as follows. Actually, maybe 1 year ago, maybe 15 years ago, I spent a lot of time of doing something called categorification, when we replace numbers with categories or something like that. And in algebra, topology, whatever. But then, maybe last year, I realized that there should be lots of isizations and implications in mathematics, whatever it can be. So, for example, if you see that can replace numbers with games, so there are lots of game theory, then we can create something to be called ludificatio. Ludificatio in the sense that we replace numbers with games with all consequences. Maybe I just suggested the term, maybe it should not be, but I'm pretty sure that whenever you have a nice part of mathematics, which need not be a structure or category in a pure, in a rigorous mathematical sense, the less rigorous it is, the better we should, the more rejoice we should get.
Well, then you're not getting anything out of probability theory because.
Yeah, no, I'm asking you the following. So maybe we can take. So you see, we can replace numbers, or so I think you were thinking of
It's. Yes. Хорошо, хорошо.
Да, предположим, что вы занимаетесь какой-то вашей любимой прекрасной математикой. Ну, скажем, вот для меня там порядок многообразия, порядок галактических фунтов. Я их строю со значениями числа. Но я знаю, что вот есть там такая наука, такая наука, такая наука. И мы можем перейти от того, что там знали в античности, к тому, что привели к каким-то другим там, категориям, каким-то понятиям и так далее. И вот мне пришло в голову слово модификация. Значит, попытка сделать из чего-то игры. Я пока еще не доказал никаких теорем, не написал статьи, никаких статей. Но у меня вопрос, а может быть можно сделать какой-то, я не знаю, probabilization, я не знаю, как это правильно, probabilization, не знаю, как это назвать, но, в общем, вопрос такой, значит, пусть мы строим какие-то объекты на структуру, вот люди могут переходить от чисел к размерностям, от чисел к векторным пространствам, от чисел к расслоениям, от чисел, там, не знаю, какая теория, чем угодно, там. Каждый мыслит на своем языке. Но вопрос, можно ли переходить к каким-то объектам, там, где есть случайность и независимость, где есть вот то, с чего ты начал. Вот такой вот.
Это вопрос не ко мне. Это вопрос не ко мне. Я не знаю, не могу ответить на этот вопрос.
Ну, как-то это надо прочитать, тем более, что,
Не могу ответить.
как говорится, всегда записан, и может быть кто-нибудь через там, 3 дня или через 20 лет
Ну, это точно.
послушает нашу запись, которую мы ни от кого не прячем. Да, через 3 дня или через 20 лет скажут: о, вот мы тут придумали там что-нибудь.
Нет, это вопрос.
Так что, в общем,
Вопрос не
я сторонник того, чтобы задавать вопросы. Даже
Это
если не
точно.
знаем ответа.
Я тоже стараюсь. Так, ну что, перерыв 2 минуты, да, делаем тогда?
Ну да,
Я-
я-
2 minute break. А я чай с ним могу. Тут же вроде, Руслан, тут же вроде есть этот чай.
Близкая машина, можно.
Да, вот пока что так.
Да. Well, so we have some overseas colleagues, and I know that in Western Asia, in Eastern Asia, it's a dark night now, a dark winter night. But nevertheless, please prepare as many questions in the chat as possible. So please, so far, we had a very good lead discussion. So please write as many questions so that we can communicate them to the speaker and he answers. So we really expect to have something in the chat. Пожалуйста, пишите ваши вопросы в чате. Пожалуйста, пишите ваши вопросы в чате, и я уверен, что Александр, I'm sure that the speaker will answer your questions. So after the break. Okay. I muted my microphone. Just write your questions on the chat.
So please write as many questions on the chat as possible. So please, so we expect, so you see, the speaker is very open to whatever sorts of questions, both mathematical and historical and philosophical. So please don't hesitate to ask any questions.
У меня вопросик там написал. Василий Олегович, я вопрос там написал. Можете глянуть, пожалуйста.
Насколько может увлечь? Okay, so we are.
We will proceed.
So we are ready to resume, so maybe I ask whether there are any questions.
Comments?
So there is a question. Определение из Большой советской энциклопедии. Вероятность математическая, числовая характеристика. So вопрос. Слово probability в том числе можно перевести как возможно. Possibility.
Сейчас вопрос.
Выходит, что определение ссылается на само на себя. So the question is, the word probability can be translated as possibility. It turns out that the definition relies on.
Well, but this is precisely the point. Excuse me, but this is an excellent question. This is quite precisely what we are coming to. This is excellent question. In fact, this is excellent question. This is famous paradox of probability theory. Thank you very much for this question. It is a very excellent question because what is the paradox of probability theory? When I say that if I toss the coin 100 times, there will be roughly half as many heads as tails. What does this actually mean? Does this actually mean that it is very improbable that I toss a coin 100 times and there are 75 heads? What does this actually mean? This means that if I toss a coin 100 times, and this 100 times I repeat 500 million times, then among these 500 million times, there will be very probably only very, very few. It's possible to say how few situations when there are 75 heads. But what does this mean? This means that if I repeat this tossing, this 500 million repetitions of this tossing scheme 500 billion times, then and so on. So the probability is precisely defining itself. Just let me finish the sentence. Defining itself through itself. Defining itself through itself. So there is to explain what probability means. There is this bad infinity. There is this multiplication of infinities, multiplication of numerous traces. So there is a paradox. There is a paradox in probability, and this is precisely what we are coming to. Yes.
I think both words, probability and possibility originate from Latin verbs meaning to put, because probare and putare was possible. Молодец, класс.
Absolutely.
Translate to Russian and English origin the Russian.
But in short, this event, as you say, this paradox that probability is defining itself through itself, it is very clear. And also, and moreover, even more, it is very nice that something is improbable. How do I derive from this that it will not happen to me? It is very improbable. But the fact that I enter this room at such and such precise time, at which I entered it, is also very improbable. I could have entered it 10 seconds later or 10 seconds earlier. In actual fact, with Ruslan, we had difficulty finding a vending machine for a coffee that would work. So, which is why. But how to say, in any event, just for some reason, I could have thought for 5 more seconds. So it was very improbable. Let's imagine that I entered this room at exactly 5 minutes, 17 seconds plus available. But it was very improbable. And yet it happened. So how do I know? So when in practical considerations, I use the maximum, improbable events do not occur. So this, after all, when I use probabilistic reasoning, the idea is the following: improbable events do not occur, but improbable events occur all the time. So the fact that each of us was born was an extremely improbable event. There are like billions of, spermatozoids. So it was a very extremely improbable event. So why does probabilistic reasoning actually work? Because probabilistic reasoning, it works in practice, and everybody knows that. Probabilistic life insurance famously is born in Genoa because famously ships went, I think, to Africa, and 1 in 10 ships did not return. And clearly, sailors wanted to have an idea of what would happen should they die during the journey, otherwise what would happen to their wife and children. And just on the other hand, the benefit, so 1 ship in 10 did not return, but the benefit that the other ones brought was so immense that it made every sense to insure them. But excuse me, precisely what should such premium be? What quantity, how should they compute this? So probability, well, the shipping did continue, trade with Africa continued, so it did work. But the question is, why does it work? It's very interesting paradox. This is paradox one can discuss all one's life. But precisely, and I'm precisely coming to this. So the point, yeah, did you have a question there?
Wait, just remark, no question. The wind can be random, and random cases.
Wind actually is random. If you look at simulation of wind, it looks a lot like Brownian motion. If you look at such simulations, are easy to Google. It looks a lot like Brownian motion. Yes, so what?
So maybe if let's say about the ships in the ancient times that moved just by wind.
No, there were many reasons. No, it's not because of wind that didn't go back. There were many reasons. There were pirates. There were many illnesses. There were many reasons. It was just the wind itself. There were many reasons. It was long journey. There are many reasons. Okay, so the very point, why is probability theory so effective? And this is the question that was a matter of huge debate in around the turn of the century. Debate that was, I emphasize, largely disjoint from the other debate, which was also raging in mathematics of the time, around Kolmogorov time, and which is the debate about foundations. There was a huge debate about foundations. Does the continuum exist? What does it mean? All real numbers. But these famously Markov Jr., we mentioned, it was his very point that he did not like real numbers. If you said a real number, he was sure to correct you. He was sure to tell you that it didn't exist. There was famous story, just dramatizing it a little bit, and when at a conference, he said, so we work over the field of real numbers, and I asked what? Said, what do you mean by real numbers? And the speaker asked her about what it usually meant. And I said, but this is not Markov Jr. Senior. Markov Jr. said, well, but real numbers don't exist. And Kolmogorov said, like, please stop. And there was big quarrel. There was big scandal.
Well, I think Kolmogorov did not like complex numbers.
Well, but this is separate discussion. Okay, well, in any event, so the setup for Kolmogorov's axiom. So there is this big philosophical discussion about what is probability. What's probability to understand is good. So this what is probability that such number? What is probability that such number has such partial quotient? have position of number and continuous fraction. Yeah. What is the probability that this number is, let's say, 7? What is the probability? This is very interesting mathematician, Gulen. Gulen, a mathematician who was born in the Russian Empire in Helsingfors, and just then moved to the observatory in Sweden, and who was an astronomer. So he got into these questions from celestial mechanics, from considerations in celestial mechanics. Okay, so people who the question of formulating mathematical axioms for probability theorem, it was a Hilbert problem. Hilbert formulated this problem in Paris, I think number 6. So there was an attempt by Sergei Epstein. Epstein's attempt was nice, but nobody's using Epstein's axioms. And well, there are several reasons for this. Epstein didn't go far enough, but there is another reason which I will mention. Epstein was trying to explain what it is probability. And in this, he is joined by Richard von Mises. A scholar of great versatility, by the way, a scholar of Rilke, a famous expert on poetry of Rainer Maria Rilke. So Richard von Mises. So von Mises describes what is called frequentist approach to probability. What does it mean, probability? It's a description of experiment which you can repeat a lot, many times.
Well, I would be very happy to organize a sort of seminar concerning Rilke and Russian poetry. I'm very fond of Rilke.
Yes, but this will
Yes,
yeah, but this will not be today. Yes, this is in fact interesting subject, but not today. So just he says that probability, we have experiments for which which we can repeat many times. Well, like tossing the coin, and well, then we have the frequency of the event that suits us. And then there are all sorts of discussions. Obviously, there is the problem that what if you only consider those times at which it falls tail? When you say there is an experiment which is repeated infinitely many times, nice. But let me only count the times when it falls tails.
well, there is a question from the chat.
Yes.
What do you think that probability and possibility are synonyms? Probability and possibility are there synonyms?
I don't think I can answer this. Let's go back to Kolmogorov axioms. So precisely von Mises, how to say, the approach of von Mises and Bernstein is the approach of trying to understand when, in what kind of trials it is possible to think about probability. And again, and there are subtleties. Again, as I say, when von Mises says that let's consider those trials that we can repeat infinitely often. Well, yes, but those trials in which tails fall tails, we also can repeat infinitely often. So what? So then probability is maybe 0, maybe 1, maybe 1. Okay, so but both Bernstein and von Mises, for them it is objective probability. It is objective probability. Completely different picture is by Definetti. So Definetti He is a little bit later than Kolmogorov, but to a very large extent independent. Bruno Definetti, he starts very ready. He says, probability does not exist. Probability does probability does not exist. So Bruno Definetti is precisely a representative of the subjectivist school, and he traces this to Poincaré. That probability is a statement about me, not about the world. It is about my knowledge. It's a statement that my knowledge is not sufficient. I don't know. In fact, if I had greater knowledge, then it would be possible to say precisely whether the coin would fall this way or that way. It's because my knowledge is imprecise, I don't know. So probability is pure for Definetti as for Poincaré. Probability is purely subjective. It's subjective. There is no probability. It's just a statement about me. It's not a statement, it doesn't exist. It's just a statement about my judgment about the world. In fact, I have to make decisions. So my probability is different from your probability. I make decisions, but I don't make the same decisions as you. So probability depends on the agent. Specifically, probability depends on the information which the agent has. Well, this statement is true always. So these are the three predecessor. So I would say predecessor, alternative, and opponent of Kolmogorov. So now comes Kolmogorov with his famous axioms. So what is so new? One could ask about Kolmogorov axioms. Let us recall that what Kolmogorov axioms are that we start with space endowed with a sigma algebra measure. It's a sigma additive normalized measure, and random variables are just functions on the space. Let's say P1 or in Z or in C, doesn't matter. So Bernstein would immediately counter-argue, would immediately object. Have you ever seen a probability space? So what does it mean, probability space? So probability space, it is the space of all possible worlds. And then probability is a measure on the space of all worlds. This is nonsense. Nobody has ever seen such a thing. So Kolmogorov's foundations of probability, as opposed to Bernstein, for example. So please let me emphasize, this is not philosophical distinction, this is mathematical distinction. This is mathematical distinction. Bernstein suggests, and many other people, not only Bernstein, but many other people suggest that one shouldn't work with random variable, one should work with distribution of the random variable. Everyone knows what is distribution of the random variable. So distribution of the random variable, so in this statement, we just have push forward on R, or if you have a multidimensional random variable on Rn, or maybe R infinity, it can be the space, it can be the space of continuous functions. I emphasize again that theory of integration in infinite dimensional space was already, to some extent, started, initiated by Percy-Daniel. So it's not that the famous Kolmogorov theorem is Percy-Daniel, is also the also sometimes called the Kolmogorov theorem, and there is some indication that Percy-Daniel does consider very similar sigma algebra, very similar measure in infinite dimensional space. So for Bernstein and for many additions, so distribution of random variable is something that you see the outcomes of experiments. But random variable is defining the space of all those worlds. You never see this. So Definetti, in fact, not even made this right Bernstein. Definetti says, but this does not have any meaning. This probability does not have any meaning. This is criticism often proposed against the Kolmogorov axioms. Kolmogorov axioms are very counterintuitive. The notion of probability space is not immediately present in the intuition. There is nothing in our intuition that corresponds to a probability space, to this set of all possible worlds. It's a very complicated philosophical construction. It's if you wish, a philosophical intuition, it's not a physical intuition. So Kolmogorov functions are unphysical. On the other hand, so Bernstein tried to axiomatize probability. So probability has to have such and such property. Well, clearly, for example, probability of a bigger event is bigger, and so on. So if there is an event, and so probability, as Bernstein himself writes, probability that a child is born is higher than the probability that a boy is born. Things like this. Kolmogorov just does not want even to get into this. What does it mean, probability theory? Why probability and so on? Probability is a measure. It was sort of clear to her. The axiom of denumerable additivity, it was more or less there. But the point is that Kolmogorov completely abstains from any philosophical discussion about the meaning of probability. Let me try to illustrate my point by some example from geometry. When we talk about straight lines in geometry, there are all sorts of philosophical questions. Does the continuum exist? You know, of course, when I say it's possible to take this table and cut it into two, and then cut it again into two, or let's say this piece of this pair, and again into two. But then at some point it will become so small that it will not be possible to cut it in two anymore, so the continuum doesn't exist. Or, well, but in fact, one can argue until the end of time. But this is completely random, and this is not what one discusses in geometry textbooks. Is the space empty or not? Fantastic question. But this is not what we discuss in textbooks about geometry. So, what is a number? What does it mean? Two. What is it? Excellent question. Or by the way, what is triangle? What is triangle? It's, by the way, if you think this is not meaningful, it is very much meaningful. It is very much meaningful because what is triangle? Just, I'm not joking. What is triangle for you, Dasha? Please, what is triangle?
Yeah, yes.
Хорошо, отрезок. Что такое отрезок? Хорошо. Прекрасно. Уже хорошо, отрезок. Не, почти как еще число. Тогда, конечно, ну вот, не, да.
Естественное пространство будет, наверное, естественно.
Прекрасно, прекрасно, очень хорошо. Значит, прямая это множество. So, if you tell me that so a triangle is a set, you already have answered my question. This is not the only possibility, because the other possibility is to think the triangle is a set modulo isometries. The triangle is an arrangement of. So, for example, when you say the triangle is given by its lengths and its angles, it is not a set. It's a set modulo isometries.
Yes, and here we have a difference, as we were taught at school, that there are equal triangles, which is wrong, and some say that we have contrary.
But just but this is my point. So triangle can be defined. This is exactly my point. You can think that there is nothing more useless than discussions about whether triangle is a set or a set modulo isometries, but you can think this just before you start writing a textbook.
You see, when you say, so now we point to the notion of homogeneity and maybe to a Kleiner, Lange, and Faulkner, but well, at some point we can get to the other way of thinking. So from the way of thinking that we are restricted to a subset of a given set, we can say that the object exists by its own. And when we pass
to the way that our object can exist by its own. We can say, for example, that a triangle is a simplex, and we can get to another category, to another way of thinking.
I'm just trying to say that there exists even in thinking about what to write in the textbook about a triangle, there are different possibilities which are realized in different Russian textbooks. In some textbooks, a triangle is, well, obviously one doesn't write to children in this language, but still it is clear what is actually written. In some textbooks, triangle is a set modular isometries, whereas in other textbooks, triangle is a set. So, but my point is that geometrical figure, is it a set? So even in some old textbooks, there is this locus. Geometrical figure, is it the same as locus or not? Okay, but I'm just trying to say that okay, but usually what is a number? So what is a triangle? It is discussed to some extent in textbooks about geometry. But what is a point is not subject for that. So what is a point? So Euclid says a point is something that does not have parts. But for one thing, some people say that maybe it's not Euclid but a later edition. And for another thing, it is clearly not these first definitions are clearly not part of the main text of Euclid. They stand apart. Similarly, what is a number? What does it mean in number? Nobody discusses it in science. What does it mean in number? Nobody discusses it. So precisely, one discusses relations between numbers, real numbers, complex numbers, rational numbers, and so on. But what is a number? This is a question for a philosopher, not for a mathematician. So precisely, Kolmogorov says, what is probability? This is not a question for a mathematician. This is not, I'm not going to discuss this. There stay discussing this and for me to discuss it, I'm not going to discuss this. I just say probability is a measure, period. For example, especially when we deal with conditional probabilities, this becomes much subtler. So you can think that this is, so for conditional probabilities, for example, something like this, if a point is chosen at random on the unit sphere and it follows the equator, what is the conditional distribution of the equator? This question, so the fact that the correct answer depends on the definition, because conditional distribution can be defined one way, can be defined in another way. This was to say the least. Namely, conditional distribution can be defined in such a way that distribution of height, for example, is uniform. Or one can define the definition in areas. There are many different ways. So, in short, my point is that the fact that, let's say, that there is no set probability, but all measures are, from mathematical standpoint, equally worthy of study. This is the very point of the Kolmogorov axiom.
Yes, for me, it's a way to avoid whatever sort of category, because making categories of whatever, making categories kills mathematics. So we want to get to a larger object. We want to get to a larger word. But we can, when we want to get to a larger word, we can start defining it a la Bourbaki. And if we start defining it a la Bourbaki, then we should face lots of questions we don't want to face. But if we allow ourselves lots of degrees of freedom, I think we will be happier.
Well, certainly, it is very clear that Kolmogorov axioms gave a lot of happiness, and that's exactly what I'm coming to. But let me just emphasize that these points were all of them very much not obvious. So the problem had been formulated by Hilbert. These people, they were very smart. The point, so this very precise division allowing, so first of all, as I say, it goes beyond physics. It has this very very esoteric object, probability space. Very beautiful, very esoteric. It requires infinite dimensional space for any meaningful construction. Any meaningful probability space is infinite dimensional and very complicated and so on. But in fact, it is a fact that it is much more convenient to work with such objects. It is much harder to work with just distributions of random variables. In fact, I will illustrate this. I will illustrate this just a little bit later.
So maybe you can make some time limits for your.
We're getting there. We're getting there. And just on the other hand, he's not engaging in any philosophical discussion, which he will later in life, This is what I will conclude with. But this precise way of treating probability theory turned out to be exactly the right way, as we can see from an immense flourishing of probability theory after Kolmogorov's book. So let me say that from mathematical standpoint, the main novelty of Kolmogorov's approach, of Kolmogorov's general measure theoretic approach, and which is not possible using the approach of Stein, for example, is the treatment of conditions. So using this, the Kolmogorov, so conditioning corresponds to taking a smaller sigma algebra. So it is small. So in my space, I have a smaller sigma algebra. It is most useful to think about this in the following way. If omega is the set of, let's say, all possible trajectories of a plane. So the plane, it evolves in the past and the future, if in past and the future. So the sigma algebra responds to events which only depend on the past. For example. Okay, another way, it's information that I have after given moment. So then what does it mean expectation? What does it mean conditional probability? Conditional probability with respect to such and such event of measure zero, with respect to such and such future. Well, in fact, Kolmogorov says this is random negative derivative. This is random negative derivative. This is random negative derivative. So, and in fact, this can be given a very simple geometric interpretation in terms of Fubini theorem. Just if I have square, for example, and my sigma algebra is the sigma algebra of sets consisting of vertical intervals.
Well, I think people stop understanding because, well, some of us learn random negative way.
But that's precisely why I'm illustrating it in elementary way. So just the conditioning corresponds simply to integrate. So conditioning means there is some event here. Okay. So conditioning means just integrating over the relevant part of the event. So I get a function, I get conditional probability is a function. Well, it depends on what I'm integrating, or it's a function which gives precisely the measure of the intersection. And I'm sorry, and this, by the way, this geometric theory of conditional expectation was developed by Kolmogorov.
Vladimir Anatolyevich,
Yes, yes. So was not very often. So from mathematical standpoint, the main novelty of Kolmogorov's book was treatment of conditional expectations. One, and the Daniel Kolmogorov theorem about existence of measures in interdimensional space. This was completely general scheme, by the way, with very non-trivial proof. There is very non-trivial proof about extension of measure in interdimensional space. There is a subtle point there. This was the main novelty in mathematics. So now I come to the heritage of Kolmogorov's work. I give only two examples, and then I explain how Kolmogorov, in the very end of his life, returned to this work in a different way. So I give two examples. So the first example is Turing. So Alan Turing, started as a probabilist. He started as a probabilist. So his first work is in probability theory. In fact, Turing heard lectures in Cambridge about law of mistakes, law of errors, the Gaussian law of errors, and he wanted to prove this. And of course, Turing did not know. This was what Turing actually proved is exactly what you learn in your standard probability course as Lindeberg theory. Lindeberg was there earlier by several years, by maybe 6 or 7 years, I don't remember exactly, but in fact, nobody in Cambridge knew about Lindeberg, and nobody could tell young Turing that in fact this was known. He did it completely independently. The work of Turing is digitized. You can in King's College, you can get it, and you can see what it is. Probability theory without Kolmogorov. Even to formulate the central limit theory. So how does he formulate the central limit theory? He said, let us consider some function, let us consider convolutions, let us then consider scaling and so on, and then they converge to Gaussian density. So it's very complicated. It's very complicated. So just reading the central limit theorem in Turing was a very brilliant man. But he certainly, he certainly could not come up with Kolmogorov axioms. So he didn't. So it was very complicated. It was very complicated. So, and the second part is Ito. So, and Ito came to Soviet Union several times. Ito, and it's...
Am I right that Ito was the first recipient of the Gauss Prize?
Probably, yes.
Yeah, so he was very old and he worked in Japan during the World War.
Well, that's exactly what I was.
Yes.
So Ito, he was a student in Japan, and he said that there are many, I heard this, I don't know if this is written down, but I heard this both from Russian mathematicians and from Japanese mathematicians, so the oral tradition is very consistent. So Ito said that he was reading papers of Levy and he could not understand it. And then he saw the book of Kolmogorov and immediately could understand that. And then Ito was in Kyoto. And by the way, everybody in Japan was really afraid that Kyoto would be bombed. So there was a lot of fear that Kyoto would be bombed. In actual fact, it wasn't, but there was a lot of fear. So he was there in Kyoto and he was inventing his integration theory based on the book of Kolmogorov. And I just want to conclude by saying that towards the very end of his life as a mathematician, then he had a long life as an educator. Towards the very end of his life as a mathematician, the last work of Kolmogorov, last cycle of precisely he goes back to the question that von Mises discussed 50 years before that, 30 years before that, the question is, okay, this is very nice, special theory and so on, but I have only one life. I have only one sequence of events. What does it mean, one random sequence? One random sequence. What does it mean, one random sequence? And the answer to this question is the concept, the last great discovery of Kolmogorov, the concept of Kolmogorov complexity, and about this maybe we talk another time. Thank you very much.
Yes, so thank you very much. If there are very short questions on the chat, you may look, but otherwise, I think it's a bit late. So please, any short.
It's not that late though.
Well, somewhere, if it's not, somewhere it is. It depends on, maybe if someone is from Kyoto, maybe it's a bit late. I don't know.
Surely in the land of Ito, people work late.
So, Sasha, yeah.
So questions on Zoom?
Есть вопросы.
Вопросы в Zoom?
Так, но если вообще подумать, невероятность и возможность — это синонимы. Это последний вопрос от Вера Пушкина. Школа города Харькова. Мы ученики из Харькова.
Отлично.
А вот, да, так что вот.
Да, Илья, но я думаю, что все-таки вероятность и возможность это не синонимы. Но давайте это обсудим.
Значит, Саш, с огромной радостью мы ждем тебя на всех наших семинарах. И кроме того, у нас есть математический кружок. Можно рассказать все, что угодно. И...
А где он этот кружок? Это онлайн.
К сожалению, онлайн пока что просто...
Нет, когда будет лично занятие.
Ты онлайн делаешь?
Не делаю.
Не делаешь. Ну, хорошо, ладно. В общем, портрет Москва, Пекин. Ну, да, вот я в Пекине 4 года назад, сейчас пока что он онлайн. Поеду туда, позову тебя.
Давайте делать.
Ладно, хорошо.
Thank you very much, everybody. Thank you for your patience.
Thank you very much for a great talk. Роман, пожалуйста, есть запись.
So if any further questions, you can always write me or write Vasa, and I will answer.
Запись доклада, пожалуйста, пошлите.
Да, пожалуйста.
Все наши, ну, я вам тоже, возможно, интересно, пожалуйста, свяжитесь, вот, пришел к нам коллега,
Андрей.
Да, Андрей, вот, пожалуйста, пошлите всем нам, и, соответственно, мы туда добавим огромное количество сумасшедших вопросов.
Это правильно. И комментариев.
Если у нас много на полях, и все это обсудим, я могу спасибо тебе, Саша, за прекрасный да.
Спасибо.
Да ладно, всем,
Спасибо, Лев.
всем доброго времени.